Assalamualaikum dear students. Today we are going to learn another test for convergence and divergence of the series, which is called comparison test, and this covers the section 10.4 of the book of course of chapter 10. So in this lecture we are going to learn two types of comparison test. First is called direct comparison test and the other is called relevant comparison test. So as the word comparison says, or reveals that we are going to compare two series. So we have seen how to determine the convergence of geometric series, P series and few other series. Now we can test the convergence of many more series by comparing their terms to those of the series whose convergence is already known. So let's see how. Uh, so theorem number 10 actually gives the answer of this question, and in this theorem we are going to state direct comparison test and we are going to prove it as well. So if we have two series sigma an and sigma bn with the relation bn is greater or equal to an and both are greater or equal to 0, that is a and bn both are non-negative or positive, then if bn converges, that is sigma bn converges, that is that the series with greater terms, larger terms converges, then the series with smaller term also converges. Number two, if the series with smaller term diverges, then the series with larger term also diverges. So let's prove both of them. And in order to prove these two results, we are going to use a result, a corollary, which we learned in the previous section 10.3, and we used it to prove different results as well. And this corollary states that the series sigma a and bn converge if and only if their partial sums are bounded from above. Alright. So in part 1, what is given in this case? Given is that sigma bn converges. If sigma bn converges, we have to prove that sigma an also converges. So let's assume sigma bn converges, and if it converges, then it must have some value. So let it converge to the number n. Okay. Now, what is the relation between the sigma bn and sigma an? Let's consider a partial sum of sigma, this series an. Let consider the partial sum. So let Sn be the partial sum. Then Sn is equal to a1 plus a2 plus an. And using this inequality, this is less or equal to b1 plus b2 plus bn. And this is less or equal to sigma bn, because this is the partial sum, so this is less or equal to the actual sum of the series. So this is less or equal to sigma bn, and we have assumed that the sigma bn is equal to n. And what does this mean? This partial sum a1 up till an is bounded above. Now, if this partial sum is bounded above, so according to this corollary, the series sigma an converges, right? So what we have proved that if sigma bn converges, then sigma an also converges with the condition bn is greater or equal to an and both are greater or equal to 0. So let's try to prove the part 2. So in part 2, we are given a divergent series, which is sigma an. That is, the series with smaller terms is divergent, right? So if sigma an diverges, then sigma bn also diverges. We have to prove that sigma bn also diverges. Now, let's assume sigma an diverges, and we have to prove sigma bn also diverges. Then suppose otherwise, that sigma bn is not divergent. Okay. So what does this mean? If sigma bn is not divergent, it means this is convergent. There is no other option. If this is convergent, then its partial sum must be bounded from above, right? So let's consider the partial sum. b1 plus b2 plus bn, and because of this relation, this is greater or equal to a1 plus A2 plus AN. Now, since due to our assumption this is bounded above, say this is less than some number k, if this is bounded above, then this should also bounded above because this is less than this sum, right? Now, if this is bounded above, this means sigma an is convergent, which is actually contradiction to the fact that sigma n diverges. So, our assumption that sigma bn converges is not right. This is wrong assumption. So, we conclude that if sigma an diverges, then sigma bn also diverges. Okay, let's apply this theorem in order to determine the convergence or divergence of the series. So, first example, we have this series sigma n raised to 1 to infinity 5 over 5n minus 1 over 5. So, because we have n in denominator, that is a linear polynomial in denominator, so we can compare it with 1 over n. And sigma 1 over n is divergent series, so we know that. Okay, so what is the relation between 1 over n and the nth term of this series? So we can see that 1 over n is less than 1 over n minus 1 over 5. That is, this is an, this is bn. And if smaller series is divergent, then the series with the larger terms is also divergent. Now, since sigma 1 over n is divergent, so sigma 1 over n minus 1 over 5, that is 5 over 5 n minus 1 is also divergent. So, using part 2 of the theorem 10, we can conclude that this is divergent series. Now, next series we have sigma 1 over n factorial, n varies from 0 to infinity, so each point here is 0. And the term-wise expression of this series is this. So first term is 1, second term is also 1, third term is 1 over 2, fourth term is 1 over 6. So we can compare this with the series like 1 over 2 to the power n, which will give us the terms like 1 plus 1 over 2 plus 1 over 2 square, that is 4, 1 over 8, and so on. Now, let's compare it with the terms in this series. So its first term is 1, its second term is also 1. So we can add 1 here. So 1 plus, so that we can have first two terms equal. So 1 plus sigma 1. So now first term is 1, so both terms are equal. Second term is 1, so both terms are equal. Third term 1 by 2, both terms are equal. Fourth term, we have 1 over 6 here, we have 1 over 4 here. That is, 1 over 6 is less than 1 over 4. So this series is less than this series. Or next term 1 over 4 factorial, that is 1 over 24 is less than 1 over 8, and so on. You can see that 1 over n factorial is less than 1 over 2 to the power n for all. So what we did, we found the sum of this series. Because this is geometric series, we can find the sum and its common ratio is less than 1. So this is convergent, right? And the sum of this series is 3. So this given series is bounded by 3. So it has an upper bound. It's every partial sum is bounded by 3. So it has an upper bound. So that is why we can say that. And the 1 over n factorial is less than 1 over 2n. So using part 1 of the theorem 10, we can conclude that since this series is convergent, that is, the series with greater terms is convergent, therefore series with smaller term is also convergent. So using part 1 of the theorem 10, we conclude that this given series is convergent series. And do not forget that this does not mean that this series is equal to 3, the sum of the series is equal to, or this series is converges to 3. This is not the case. we just conclude that this series is convergent. Actually, this given series is convergent and converges to 3. But this series is uh, not equal to 3 or does not converge to 3. So this is the point to be noted. Do not forget this. So we can just conclude that using part 1 of the theorem 10 that this series is convergent. So right now we don't know the number it is convergent to. Alright, C part. So we have another series. C. Okay. 5 plus 2 over 3 plus 1 over 7 plus 1 plus 1 over 2 plus square root of 1 and 1 over 4 plus square root of 2 and so on, right? So if we ignore the first 3 terms because they are not going to the with the pattern of the rest of the terms. So and you know that deleting and adding finite number of terms does not make any difference in the convergence and divergence of the series. So we can add and delete finite number of terms from the series. So if we have this series, now you can see that what is this 1 plus 1 over 2 plus square root of 1 and here is 1, right? So plus 1 over 2 square root plus square root of 2. So 1 over 2 cube plus square root of 3. So you can see that plus so on. The nth term of the remaining series is this. Now if we compare it with the series 1 plus 1 over 2, just forget this additional part, plus 1 over 2 square plus 1 over 2 cube plus 1 over 2n. Now just pause and think which series is greater. So I will answer it after a while. Okay. I hope you would have figured out which is greater and which is less, which series has greater terms. So just compare the first term of both the series is same. Now in this case, denominator is 2. In this case, denominator is 2 plus some positive thing. That is, this term is less than this term. That is less than this term. Now in this case, 2 square, denominator is 2 square, and here we are adding something in 2 square, something positive in 2 squares. So in this case, denominator is greater than 2 square. That is, this term is less than 1 over 2 square. Similarly, this term is less than 1 over 2 cube. Similarly, this term is less than 1 over 2n. So in general, we can say that 1 over 2n plus square root of n is less than 1 over 2 to the power n. Right? And we know that this series is convergent because this is geometric series. So we can say that. So this series is convergent. Since this series is convergent, then this series is also convergent using part 1 of the theorem. Right? So this is how direct comparison test helps us determine the convergence and divergence of the series. Okay, next, limit comparison test. So we now introduce a comparison test that is particularly useful for the series in which an is a rational function of n. That is, the nth term is the rational function of n. So let's see how can we use this and how can we apply this and how do we define this actually first of all. So theorem 11 states the limit comparison test. And suppose again comparison is involved, so we are going to have more than one series. Suppose that an is greater than 0, both are positive. See, an is greater than 0 and bn is greater than 0 for all n greater or equal to n, where n is an integer. So if limit of an over bn, that is the quotient an of an and bn, limit of an over bn as n approaches to infinity is c. C is any number and c is greater than 0, right? C is greater than 0, then sigma an and sigma bn both converge or both diverge. If we know one of the series is convergent, then other will also be convergent, and if we know one of the series diverges, then other series will also diverge. So secondly, if limit of an over bn as n approaches to infinity is 0, then sigma bn converges. This one. Sigma bn converges, then sigma an converges. And sigma bn. That is, if this limit is 0 and we know that sigma bn converges, then sigma an also converges. Now, third case, if limit of this quotient an over bn and approaches to infinity is infinite, then and sigma bn diverges. That is this series. If and sigma bn diverges, then sigma an also diverges. Right? So there are three cases. If this limit is infinite, if this limit is 0, if this limit is c other than 0 and infinity, that is c greater than 0. If, and it will be greater than 0. It cannot be negative because a and b and both are positive. So c less than 0 case is not possible. Right? So c is either greater than 0 or infinite. So negative limit is not possible because an is greater than 0 and bn is greater than 0. Both of the terms are greater than 0. Okay, so let's prove this. First part. So we are going to prove part 1. I'll give hints of part 2 and part 3. You can complete the proof on your own. So first of all, since c is greater than 0, now what is given? Limit of an over bn as n approaches to infinity is equal to some c, and c is greater than 0. Now since c is greater than 0, c by 2 is also greater than 0. Then there exists an integer n such that an over bn minus c is less than c over 2 whenever n is greater than n. So what does this mean? This inequality can be written as minus c by 2 is less than an over bn minus c less than cn by 2. Okay, so this inequality can be written in this form. Now just add c in every term of the inequality. So by adding c here we have c by 2. By adding c here we are left with an over bn. By adding c here we have 3c by 2. So an over bn lies between c by 2 and 3c by 2. Okay. So what we are going to do, multiply whole inequality by bn. Since bn is positive, so inequality will remain unaltered. Okay. So c by 2 into bn is less than an is less than 3c by 2 into bn. Now we are in the position to conclude something. Okay. So if sigma bn converges, then sigma 3c over 2 bn also converges, and then right series, left series both are converging, so sigma an is also convergent, right? By the direct comparison test, we can conclude this. Now, if sigma bn diverges, then sigma c over 2 bn also diverges. And what does this mean? Sigma an also diverges by direct comparison test. So, what we have proved in this case, that if limit of an over bn as n approaches to infinity is equal to c, then sigma a and bn both converge or both diverge. If one of them is convergent, then other is also convergent. If one of them diverges, then other is also diverges. Okay, part 2. In part 2, if this limit is 0, we have to prove that and if limit is 0 along with sigma bn converges. This is also given. Okay, we have to prove this sigma an converges. limit is 0 and sigma bn converges, we have to prove that sigma an converges. Now, first of all, let's start with the limit. This limit is 0. So, in this case, an over bn is bounded sequence. As a result, there exists a constant m such that an is less, since as n approaches to infinity an over bn is 0, so this means an over bn is a bounded sequence. So this result we learned in section 10.2, I guess. So as result, there is, if this is bounded, then there must be a constant m such that an over bn is less than n, because this is bounded above. Okay, so if this happens, since bn is positive, we can multiply bn by bn both the sides. So we have this inequality, and this implies if bn converges, then an converges, right? And bn converges because this is given. Bn converges. So if bn converges by direct comparison test, bn converges, then mbn converges. If mbn converges, then sigma n also converges. Okay, next part 3. If this limit is equal to infinite. So suppose this limit is infinite, and along with the result sigma bn diverges. Okay, if this is infinite, in this case an over bn is not a bounded sequence, this is unbounded sequence. Therefore, for every constant m, there exists an integer n such that an is greater or equal to mbn. In case it is bounded, the condition must hold an is less than mbn, right? Now, in this case, this is not bounded, so the condition will reverse. An is greater or equal to mbn for all n greater or equal to n. So, therefore, now given is sigma bn diverges. That is the series with smaller term diverges. What does this mean? Series by direct comparison test, series with larger term will also diverge. So this implies sigma a diverge. Okay, there are few examples to use the limit comparison test. So check whether the following series converge or diverge. So first of all, we have this series 1 over 2n minus 1. So an here is 1 over 2n. Since 1 over 2n is involved, we can compare it with 1 over 2n, and we know that the series is convergent. And but we need to show that the limit an over bn is some c which is greater than 0, right? If we are able to show this, and this is bn, by the way, this is bn. So if we are able to show this along with sigma bn convergent, then we can conclude that this is also convergent. So let's see. Let's take the limit. So limit an over bn. An is this given series, and bn is this assumed series, known series, which is known to be convergent. Okay, so an over bn is equal to limit of just plugging in the values. We have 2n over 2n minus 1, and by taking the limits you can do the manipulations yourself. So we have the answer 1. That is, we have c which is equal to 1, and this is greater than 0, by the way, and we can use the limit comparison test, and we can conclude by using the limit comparison test part 1 that this given series is also convergent, because this series is convergent. Now next we have this series log of n over n to the power 3 by 2. Okay, in this series, we can see that its denominator is n to the power something, okay, and in the numerator we have natural log of n. So, if we can find a series which is greater than this, and since we have in the denominator n to the power 3 by 2, so we can find a P series which is greater than this series. If we can find such a series, then we can compare this P series with this series. And we know that P series is convergent whenever P is greater than 1. So we have to see that, and by comparison test, we also know that if the greater series is convergent, then the smaller series is also convergent, right? So, or in the limit comparison test, we know that if an over bn is some constant as n approaches to infinity, is some constant with the condition that bn is convergent, right? Then we can conclude that this series is series an is also convergent. So let's try and find out. So because ln grows more slowly than n to the power c, so for any positive constant c, we can compare the series to a convergent p series. So to get the p series, we see that natural log of n is over n to the power 3 by 2 is less than. So denominator remains same. We just compare this natural log with n to the power n over 4, and n over 4 is greater than natural log of n. We can verify it. Now, why did we choose n to the power 1 over 4? If we choose n to the power 1 over 2, which is also valid in a way that natural log of n is less than square root of n, but in this case, we are going to get a p series with p is equal to 1, which is not convergent. So let's try a convergent series first, and then we'll see what happens. So in order to make it convergent, we need p which is greater than 1. So that is why we chose n to the power 1 over 4. So n to the power 1 over 4 is greater than the natural log of n. Now just simplify it. We have 1 over n to the power 5 over 4. That is, we have 1 over n to the power 1 plus 1 over 4. That is, p is greater than 1 here. So for n sufficiently large, an is equal to log of n over n to the power 3 by 2, and en is equal to 1 over n to the power 5 by 4. So we have now taking limit an over bn. An over bn is natural log of n over n to the power 1 by 4. Now taking limit, we have the answer by L'Hopital rule. So in order to apply the L'Hopital rule, you have to differentiate the numerator and denominator both. So by differentiating, numerator we have 1 over n, and by differentiating denominator we have 1 over 4 n to the power minus 3 by 4, right? Okay, now just simplify it. We have 4 over n to the power minus 3 by 4 plus 1, that is n to the power 1 by 4. So as n approaches to infinity, this approaches to 0. So there must be sign of equality here. So this is equal to 0. Now by the limit comparison test part 2, since Bn is P series with P greater than 1, so this converges, therefore sigma An also converges. So if we have this limit equal to 0 and Bn converges, then An also converges. So next, in this case, we have this series 3 by 4 plus 5 by 9, which is equal to sigma n raised to 1 to infinity to n plus 1 over n plus 1 square. Okay. Or it can be written as sigma n raised to 1 to infinity 2n plus 1 over n square plus 2n plus 1. We just expanded this square. Okay, for large n, we expect that an to behave like 2n over n square, which is equal to 2 over n, right? As n approaches to infinity, as n gets larger, so we can see that so when n gets larger, this 1 doesn't make much difference in 2n plus 1. So this is quite similar to 2n, and if n gets larger in the denominator, so n square is the more dominant term. So we can say that for large, very very large n, a n behaves like 2n over n square. That is, its behavior will be like 2 over n, right? So since the leading terms dominate for the large n, so we let bn over is equal to 1 over n. So we can compare this with 1 over n. Since sigma bn, that is sigma 1 over n, diverges, and this limit an over bn is equal to 2, that is greater than 0. So sigma an diverges by part 1 of the limit comparison test. We can just conclude that we can conclude that this series is also divergent, because sigma bn, which is 1 over n or 2 over n, whatever you can say, since sigma bn is divergent, therefore sigma an is also divergent, and we used part 1 of the limit comparison test. And what does this state? Let's see. So here we go. Part 1 states that if this limit is equal to c, where c is greater than 0, then sigma a and sigma bn both converge, both diverge. So if one of them is converging, then other is also converging. One of them is diverging, then other is also diverging. So in our case, one of them was divergent, which is 1 over n. So this concludes that the given series is also divergent. Okay, next. Again, check whether the following series converge or diverge. So we have the series, a little complicated series. In this case, we have 1 plus n log of n divided by n square plus 5. Right? So I leave this for your exercise. Read it and try to understand it. So we'll discuss it if you are not able to understand it yourself, but first try it yourself, and then let me know if there is some difficulty. We'll discuss it. And that's all for today.